Welcome, esteemed colleagues, academics, and curious minds. Today, we delve into a topic that sits at the intersection of technology, health, and our everyday lives: wearable devices for energy expenditure estimation. As we make strides in personal health and technology, understanding how our bodies expend energy becomes increasingly important. Today's talk focuses on how wearable devices can help us quantify this. So, let's embark on this journey together. As we navigate through this intriguing topic, here's a snapshot of our journey today. We stand at the threshold of our exploration, in the stage labeled Introduction. As we progress, this path will lead us towards energy expenditure estimation with ear-worn wearable devices, and culminate in self-supervised learning for energy expenditure estimation. As we delve deeper into our topic, let's begin by understanding a fundamental concept: human energy expenditure, often abbreviated as EE. Human energy expenditure is the energy our bodies consume to perform crucial functions, such as respiration, circulation, and digestion. Knowing our energy expenditure holds great significance in our lives. Let's explore why it's crucial. Firstly, it helps us understand and manage chronic diseases, including obesity, diabetes, and metabolic disorders, among others. By tracking our energy expenditure, we gain valuable insights into our body's functioning, enabling us to tailor treatments and lifestyle changes more effectively. Secondly, it aids in tackling issues like fatigue and sleep disorders. Knowing when and how our energy is consumed can guide our daily routines for a healthier lifestyle. Thirdly, for sports enthusiasts and athletes, measuring energy expenditure is key to designing effective training plans, monitoring performance, and preventing injuries. And lastly, in our daily lives, it provides an understanding of our physical activity levels, energy consumption, and net calorie intake. In short, understanding our energy expenditure is a key step towards a healthier and more informed lifestyle. Now that we've understood the why behind energy expenditure estimation, let's discuss the how. There are two primary methods for measuring energy expenditure. First, the gold standard methods, which include direct calorimetry, indirect calorimetry, and doubly labeled water. These are traditional and highly accurate methods, but often require complex setups and professional expertise. The second approach, and our main focus today, is utilizing wearable devices. These gadgets, equipped with embedded sensors like accelerometers, allow us to estimate energy expenditure in a less invasive and more user-friendly way. This integration of technology into health tracking paves the way for a future where maintaining our health becomes more personalized and convenient. Let's now turn our attention to the core of today's discussion: our research project. Our mission was to identify challenges within the domain of energy expenditure estimation, or EE, and then devise solutions to address them. As we peeled back the layers of these complex issues, we divided our project into two distinct phases. In Phase 1, we tackled energy expenditure estimation with ear-worn wearable devices, or as we like to call them, wearables. Phase 2 delved into a more sophisticated approach, using self-supervised learning and transfer learning for energy expenditure estimation. As we proceed, you'll get a closer look at each of these phases and the outcomes we achieved. As we journey deeper into our exploration, we now arrive at the next significant juncture: energy expenditure estimation with ear-worn wearable devices. So, prepare to delve into how these intriguing devices, which we refer to as wearables, play a crucial role in the realm of energy expenditure estimation. Now, let's explore the why behind the selection of wearables for energy expenditure estimation. Wearables leverage the skin on our ears, which improves the accuracy of embedded sensors like photoplethysmography or PPG. This uniqueness of ear skin brings an added dimension of precision to our readings. Additionally, their small size and portability make them ideal for comfortable wear throughout the day. Therefore, wearables aren't just a matter of convenience, but a strategic choice that enhances the accuracy and usability of energy expenditure estimation. As we ventured into this phase of our research, we were guided by two main research questions, or RQs. Our first research question, RQ1, asked, can wearables with multimodal sensors be used for energy expenditure estimation during various types and levels of activities? The second question, RQ2, was, how does the performance of wearable sensors compare to other commercial devices placed on different body positions? The answers to these questions formed the backbone of our research and guided our exploration in this phase. Before we go any further, let's acquaint ourselves with the dataset we utilized in our study. We made use of the WE dataset, a publicly available multimodal multi-device dataset, which was published in September 2022. This data was not collected by us but was gathered in the controlled environment of Nokia Bell Labs, Cambridge. The dataset includes readings from a range of devices including the VO2 Master Analyzer face mask, Nokia Bell Labs earbuds, Empatica E4 wristband, Muse S headband, and the Zephyr Bioharness chest belt. These devices capture data across various activities such as sitting and standing, running, and cycling. This comprehensive and diverse dataset was instrumental in guiding our research in the first phase. The study protocol for the data collection process in the WE dataset was meticulously designed. It encompassed 3 distinct types of activities: sedentary activities, such as sitting and standing, ambulatory activities, like running, and vigorous activities, represented by cycling. Furthermore, each activity was conducted at 2 different intensity levels. For instance, running and cycling were performed at 2 distinct speeds. Every activity, at each intensity level, was carried out for a duration of 5 minutes. This strategy ensured a comprehensive and diverse set of data, encompassing 6 distinct activity types. This varied and dynamic approach allowed for a nuanced understanding of energy expenditure across different levels of physical activity. As we delved deeper into our research, we conducted 3 significant experiments. Our first experiment, titled Evaluation of Wearable Devices for Energy Expenditure Estimation, involved 2 key components. We compared various algorithms and their effectiveness for E, followed by a comparison of different sensor combinations and their impact on E. Our second experiment focused on contrasting the performance of our wearable devices with other commercially available wearable devices. These experiments aimed to thoroughly assess the potential and practicality of wearable devices in the realm of energy expenditure estimation. From our study, several key theoretical implications emerged. Firstly, we found that wearable devices can indeed be utilized for energy expenditure estimation, performing comparably to other commercial-grade wearable devices. Secondly, our research indicated that in-ear photoplethysmography measurements may offer a more accurate EE than in-ear accelerometer measurements. Lastly, our findings suggest that the Muse S headband performed the least effectively in our study, implying that the head might not be the best location for energy expenditure estimation. These findings marked a significant step forward in understanding the potential of wearable devices for health and fitness tracking. We have now transitioned into the second phase of our research project. Here, we will delve into the fascinating topic of self-supervised learning for energy expenditure estimation. So let's begin this exciting exploration together. In the course of our first phase, we encountered a significant roadblock: the difficulty in gathering a large volume of energy expenditure data using wearable devices. Indeed, most datasets for energy expenditure estimation contain limited data, which can hinder progress in the field. This motivated us to explore a new path. As a solution, we delved into the potential of self-supervised learning and transfer learning approaches using accelerometer data for EE. Let's delve deeper into this exciting journey. In this second phase of our research, we are driven by 3 fundamental research questions: harnessing advanced machine learning for wearable tech accuracy, evaluating a unique model for energy expenditure estimation, and assessing dataset sizes' influence on machine learning reliability. On your screen, you'll see a visual summary of all our conducted experiments. We conducted 3 key experiments during this phase. The first experiment was to select the best model architecture for energy expenditure estimation, leveraging both self-supervised learning and transfer learning. Once we identified the best model from the first experiment, we carried out our second experiment, where we compared various methods for energy expenditure estimation using this best model. In our final, third experiment, we examined the performance of energy expenditure estimation with different sizes of datasets. This helped us understand how the quantity of data influences the accuracy and reliability of our models. Following the completion of our experiments, we have derived some critical lessons. First, there is a distinct advantage in integrating different types of models. By combining convolutional neural networks, long short-term memory, and attention mechanisms, we were able to capture both spatial and temporal accelerometer features in a way that outperformed standalone CNN or LSTM models. Secondly, our integrated approach also demonstrated superior feature extraction capabilities. We observed significant improvements over traditional methods in filtering out noise and extracting clean, valuable data from accelerometer readings. Lastly, when it comes to smaller datasets, our strategy of employing self-supervision coupled with transfer learning showed promise. It delivered comparable performance due to the utilization of previously acquired knowledge through self-supervision. This is particularly encouraging for scenarios where data collection may be limited. Now, let's dive into a brief preview of our product demonstration. We've crafted a mobile application from our research insights, aiming to redefine energy expenditure tracking with wearable technology. As we come to the close of this video, we hope that the insights shared have been both enlightening and valuable. We appreciate your time and attention, and thank you for joining us on this exciting journey of exploring energy expenditure estimation with wearable devices.